All right, everyone, we are back and we are going to do our problem set 5 solution video. So we're looking at the systems, A, B, and C, and then we're asking about, are they significantly different at this confidence level? And we're going to go ahead and let's walk through them. So we're going to be doing hypothesis testing. So we're going to have to utilize and pull out our lecture 5, excellent, which we've got right here. So when we're looking at this first question, are A and B significantly different at a 1% significance level? So this is a t-test comparison between two samples. So we're going to be using our huge, nasty equation. But our null hypothesis is basically mean of A is equal to mean of B. Our alternative is that they're not equal. Since it's a two-tailed, we're going to be using alpha over 2. So alpha is equal to 0.01 here. 4, we need our t experimental from our big nasty equation. 5, we know we're going to do t.005. Our degrees of freedom is going to have to be calculated with our big nasty equation as well. So let's go ahead and let's start to use our functions. So if we look at, and actually I'm going to pull up our exam 1 file prep. So I'm going to go here. There should be an exam 1 prep, exam 2 prep, exam 1 prep. So I'm going to use essentially these functions, and actually I'm going to start and define some values here. So I'm going to do, let's do NA, XA, SA, B, B, A, or actually C. Oops. Let's go up here. C, and C. So, number of samples from A, 12 times. The mean was 15. Standard deviation was 3. Number of samples of B, 98 times. Mean of 17, standard deviation of 0.5, and then finally system C was measured 22 times, a mean of 19, and a standard deviation of 8. Excellent. So we're going to do our t-test comparison on our new comp. I'm going to, as always, read in all these functions, define all these variables here. And so now we can go and I can say, I want to look at A and B. So XA, XB, SA, SB, A, B. And I can copy this. Order matters, so make sure that you're being consistent. This is our T experimental. This is our new comp, 11. So we can say we need to look up this value. Let's look up T.005, 11, that's going to give us 3.106. T experimental, where did we see it? I think it was negative 2.3. Negative 2.3. When we're looking at our two-tailed test, because that's what it is, are they significant? Our bounds here are plus minus, and actually let me make sure I got the right one there. Pretty sure I have, but I want to just make sure. 0.005, 11, 3.106. Excellent. 3.106 minus 3.106. So where are we falling? T experimental is going to fall minus 2.3. So we are in the do not reject. P is greater than our alpha. Or in this instance, our alpha over 2. Excellent. So there we go. What about, is B greater than C? So when we're doing these types of things, now we're going to say, is X of B greater than X? Or our null hypothesis is still the same. Is this equal to C? I could erase this. Our null will be, so that's, the null is equal, our alternative is X of B is greater than X of C. Our alpha now is equal to 0.05, and we don't know what this value is yet. We also don't know what this is. our fifth step now, instead of alpha over 2, it needs to stay here because we're just doing a right tail test. So our t theoretical value will just be t of 05. We don't know what our nu is because, again, it's b and c. So let's go ahead and let's get at it. So now it's just b and c. So we can adjust this script here. I'm going to copy and paste. I'm going to do x of b, x of c, x of b, x of c, x of b, x of c. And then b, c, b, c. Nu is 21. That value is going to give us the following. T of 05, 21, 1.721. 1.721. What's our t experimental? Oops. T experimental is minus 1.7 or 1.17 maybe. Nope, 1.17. Either way, it falls way over here. So that is a do not reject. P is greater than alpha in this instance. Great. So we can do the same thing now. We're going to kind of move a little bit quicker because hopefully now you get the picture. So now is C less than A at a 99% confidence interval. So I'm just going to focus on this. So 99% confidence interval and the left-tailed test. So T of 0.00, or excuse me, T of 0.01, my nu is still unknown. Is C less than A? So, and I'm doing that because it's not a two-tailed test. So is C less than A? And we'll just copy and paste here. C, A, C, A, C, A. And then boom, boom. So we have 29. And our T experimental was 2.09. This is a left-tailed test. So this, whatever this value is, it needs to be negative. So 01, 29. 01, 29 is going to give us 2.462. So I'm going to go back to here. Minus 2.462. Minus 2.462. And then what was our value here? It was positive. That means it falls way over here. So that, again, is a do not reject. And that is going to be P is greater than our alpha. Excellent. There we go. Does C come from a population with a mean? Okay, so now we're doing something a little bit different. So now these questions, although it's pretty much very similar. I love this functionality. Does C come from a population with a mean of blah? So our null is our x bar of C is equal to, or our mu of C, you know, actually, yeah, let's be correct. Mu naught equals mu equals h naught, you know, mu naught, which mu is equal to mu naught, which is 10 millimeters. Our alternative is it's not, because it's a two-tailed test. 3, 1% significance, 0.01 is our alpha. 4, we need to do our T experimental, which should just be, you know, x bar minus mu naught over s of x over square root of n. And then 5 will be our T. Alpha over 2, so 0.001. Our nu is just going to be number of samples now, because we're dealing with C. C was measured 20, so it's just 21. So we can go ahead and do T001, 21. Excuse me. If I divide that by 2, it's T005. Excuse me for that mistake. So T of 005, 21. That's going to give us 2.831. And that'll be plus or minus because it's a two-tailed. And then now let's calculate our T experimental. And we're going to use, now instead of this t-test comp, we're just going to use our T experimental. So it's going to be x of C. the mu or the mu naught is going to be 10 S of C N of C. And there we go. 5.26. So that's going to definitely fall in the reject. P is less than alpha over 2. Fantastic. And I'm going to do the same thing now that we kind of did previously here. So let's erase this. Let's erase this. Good. Delete, delete. So my T experimental, we'll figure out what the value is. The next problem is saying, does P from mean less than 14, 10% significant? So that means my alpha is going to be 0.1 because it's a left, and it is a left-tailed test. So whatever that value is, I'm going to have to make it negative. It is, I'm dealing with B. So B is basically going to be infinity. I can go ahead and look up that value. 0.1 infinity. That's going to be 10%. Is that 10% significance? Yeah. 10%. So that is 0.1 infinity, 1.282. Minus 1.282. I did minus because it's a left-tailed test, minus 1.282. Our T experimental, we got to calculate that now, and that's going to be, we're dealing with B. So I'm just going to copy and paste this. X of B, we're asking, is it less than 14? So our mu naught is 14. S of B, N of B, we got it. So that is going to be 59. So 59 positive. Let's just double check that number. And does that make sense? X of B is 17. Yeah, that's going to be a big difference. So that's way, way, way over here. So do not reject. P is greater than alpha here. Fantastic. Let's go ahead, erase this, erase this, erase this, and erase this. Last, does A come from population greater than? So now it's a right-tailed test. T, population greater than 16, blah, blah, blah. Doesn't give us a value, so we default to 0.05. A was measured 12 times, so my degrees of freedom is 11. T of 05, 11, 1.796. Let's go over here. 1.796, 1.796, and then let's go ahead and calculate. So we're dealing with A, and then what's the value? X of A, and then greater than 16, X of A, or S of A, everything A, minus 1.15. We're over here. Do not reject. P is greater than alpha. Done, done, and fantastic. Attached our data files. Are they significant? So we're going to work with our old data files from last time. So let's go ahead, and actually I'm going to go ahead and we need to look if they're significant. To see if they're significant at, prove, are any of these pairs statistically significant? You can do this a couple ways. You can plot it, or you can just do, you can see if they basically overlap, or you can do a, basically are they the same or not. It's 45%. Let's go ahead and do this. So I'm going to go ahead, and first I'm going to set my directory. Not like that. I'm going to set as working directory. Good. I am going to paste in here. There should only be a single column. So I'm going to have to adjust this code. Yes. So I'm going to adjust this. 1, 1. So I'm just going to run basically a t-test comparison at a 95% confidence interval. If my p-value is less than alpha, they are statistically significant. They are different. If not, they are the same. So 1 and 2, what's my p-value? 0.4, the same. Next, 0.4, the same. And then finally, 1 and 3, the same. All right, so they're all the same. So they are all statistically essentially the same because my p-value is greater than alpha, which is 0.05 or 0.025 in this instance, alpha over 2. Excellent. Now it's asking us, for data file 1, does the sample come from a population with a mean greater than 15? So a data set 1, PS41, does it come from a data set 15 at a 99% confidence greater than? So let's see. It doesn't like it because I need to set that to 1. P-value is much, much less than alpha than alpha, so we're good to go because 0.01 is our alpha. Does 2 come from a population with a mean less than 10? It doesn't say, so less than here. Good. I need to change that. I'm going to change that all to 1 right now. And then this needs to be file 3. So let's go ahead. So P is equal to 1 effectively. So, oh yeah. So that is a big old do not reject. P is greater than alpha. And then finally, does 3 come from a population with a mean of 14? So this can be two-sided. And my confidence is also going to be 95 because it's not specified. And that is going to be definitely reject. P is less than alpha over 2. There we go. That is your problem set solutions. So we'll see you next time. Thanks. Bye.